and all attendees for joining me today. It's truly an honor to present my research that forms the core of my PhD thesis. The title of my presentation is Optimization of an Industrial Centrifugal Blower Using Gradient-Free and Gradient-Based Approaches. I will begin by outlining the motivation behind this research. Next, I will present an overview of turbomachinery as well as the chosen test case for this research, followed by a brief literature review on different optimization methods with a primary focus on the adjoint method. Main and detailed objectives and numerical method related to adjoint method will be presented. Then the results of aerodynamic and hydrodynamic shape optimization using the adjoint method will be proposed. This step enables us to gain a better understanding of adjoint method before customizing the adjoint solver and applying to more complex geometries. The main part of my research related to design and optimization of forward curve centrifugal blower using both gradient-free and gradient-based approaches. And finally, my presentation will conclude with a summary of findings and future work. Turbomachines play a pivotal role in a variety of sectors, such as aviation, power generation, and maritime. In order to highlight how turbomachines are prominent in our lives, it can be referred to its global market. The global turbomachinery market was valued at about 60 billion in 2024 and is projected to achieve approximately $123 billion by 2032. Generally speaking, turbomachines consume a great deal of energy and generated unwanted noise. Therefore, designing and fabricating more efficient turbomachines is not only a need but also a must. According to International Energy Agency, achieving a 50% reduction in global emission requires substantial contribution of efficient turbomachines. 7% of this reduction is expected to result from efficient power plant where turbines play a vital role. Besides, 24% of this reduction is projected to arise from improved end-use fuel efficiency, achieved through the use of efficient turbines like compressors. An example of aviation sector can illustrate how a slight improvement in the efficiency of turbomachine can significantly reduce the energy consumption. In 2012, commercial airlines all over the world consume about 77 billion gallons of fuel. Only 1% improvement in engine efficiency of 100 Boeing airplanes can result in annual fuel saving of $2.2 million. Turbomachines can be classified based on flow paths parallel to rotational axis. In axial turbomachines, the flow enters and exits parallel to rotational axis. However, in radial one, the flow enters parallel to rotational axis and then it undergoes a 90-degree rotation. In mixed flow one, the flow exits at an angle that is between 0 to 90 degrees. Blowers, one of the most common turbo machines, enhance both velocity and pressure. but pressure rise is moderate, less that than of compressors, and they are generally designed to move a large volume of air at moderate pressure level. They have different kinds of applications, such as in ventilation and air circulation. Also, there are different types of blower, such as regenerative helical screw blower and centrifugal one. That is the chosen test case for this study. Centrifugal blowers pressurize the air and expel it out at higher velocity. They are made up of different parts. Motor generates the adequate force to rotate the impeller, which is a series of blades, and it's placed in a housing that guides the airflow. Centrifugal blowers can have different kinds of impeller, such as forward curve one. The curve of the blades are in the same direction of impeller rotation. However, in backward curve, the curve of blades are opposite to rotational axis. It is important to briefly overview different aerodynamic optimization methods. They are broadly divided into inverse and direct methods. In inverse method, there is always a desired value for objective function, which is obtained by iteratively changing the configuration. However, in direct method, there is no any desired value for objective function. The goal is to minimize or maximize the objective function. Non-gradient based method and gradient free methods are two common direct optimization methods. In gradient free methods, they globally seek the optimum, includes like design of experiments, surrogate model, and stochastic methods. In gradient-based methods, they are dependent on the information of gradient of objective function to design variable, and they include traditional methods like finite difference method and adjoint method. Inverse method can yield good design at reasonable computational cost, but it is heavily reliant on the expertise and experience of designer, and they are not appropriate for complex geometry. Almost all gradient-free methods have high computational costs, where many design variables are involved, like in turbo machines. Gradient-based method, especially adjoint method, can be used to optimize turbo machines at reasonable computational cost, even though many design variables are involved. Pinot was the first person to use adjoint approach for Navier-Stokes flows. And then Jameson brought it to field of aerodynamics to optimize different aerodynamic configuration. A clear definition of the adjoint method was proposed by Wang and He. It begins by objective function I, which is a function of U, flow variable like velocity, and the design variable alpha, like angle of attack. Equation 2 represents flow equation. Equation 3 shows the main goal of all gradient-based approaches, which is the goal to compute the gradient of objective function to design variable. And equation 4 is linearized flow equation. If we back to equation 3, flow variable sensitivity creates the problem. It shows that for each design variable, we need to solve flow equation once. So when we have many design variables, the computational cost increases. So the goal of adjoint method is to remove this flow variable sensitivity by multiplying equation 4 into Lagrangian multiplier and subtract it from equation right side of equation 3. As you can see in equation 6, by enforcing the adjoint method, we can remove the flow variable sensitivity. Then in equation 8, we have a new expression of gradient of objective function to design variable. And it's no longer dependent on design variables. Adjoint method can be divided based on how we construct the adjoint method. In continuous one, first flow equation become linearized, and then adjoint method is extracted from linearized flow equation, followed by discretization. In discrete one, the flow equation will be discretized, followed by adjoint equation and linearization. When we use the adjoint method for shape optimization, it starts by solving the flow equation and then calculate the initial value of objective function. Then adjoint equation will be solved. After solving adjoint equation, it is easy to solve the sensitivity or gradient of objective function to design variable. Based on the information from it, the design variable can be updated, and then a mesh will be deformed, and for a new configuration, flow equation will be solved again. There are many adjoint solvers like Hydra, which is developed by Rolls-Royce, and also several adjoint solver implemented in different CFD solver like ANSYS, Fluent, OpenFOAM. OpenFOAM has 4 different kinds of adjoint solver, but adjoint optimization foam is the best one since it offers a variety of objective function and boundary condition. It is developed by a group in National Open University. However, nowadays, achieving a significant improvement in efficiency of model turbo machines it is almost impossible. As an example, a blade of NASA Rotor 37 was optimized using the adjoint method, and it shows the only 1% increase in efficiency. In another study, the blade of axial fan was optimized using the adjoint method in OpenFOAM, and it shows only 1.2% increase in efficiency. This research has 2 main objectives. The first objective is to design an efficient forward curve centrifugal blower using gradient-free approaches. I used a framework that was developed before I started my PhD. So after finding the best one in terms of efficiency, it is validated against CFD simulation and experimental data. And the second objective, which is the most important one, is that optimize the efficient forward curve based on the adjoint method. So first we develop and propose a new automatic multi-objective optimization framework based on the adjoint method. For this goal, we drive the adjoint equation based on 2 new objective functions, aerolic and mechanical powers. And in order to have an automatic framework, all software are linked together using Python script. And finally, the forward curve centrifugal blower, which was initially designed by gradient-free base method, was optimized using the adjoint method. So here I want to talk about numerical method related to adjoint approach. So as different types of simulation has been done in order to avoid repetition, all software used in this research is introduced here. Salome, which is an open source software, is used as a CAD and mesh generator. Two different versions of OpenFOAM, OpenFOAM 8 and V2020-06 are used as a CFD solver. Dakuta is employed as an optimizer in only gradient-free approach optimization. And adjoint optimization foam in OpenFOAM V2020-06 is used as an adjoint solver. So the geometry and computational domain of blower is shown here. As you can see, the impeller is made up of 34 NACA blade, and also it's embedded in a very big sphere with a diameter of 1.2 meter in order to satisfy far fields. And blower is connected to exit pipe with length of 1.1 through the connector. Incompressible Navier-Stokes equation, which are closed by Kalmega-assisted turbulence model, is employed to solve flow into blower. So in order to explain how we derive the adjoint equation, we come back to the first definition of the adjoint method. In equation 8, we have a new expression of gradient of objective function to design variable. So we start from here and multiply. Lagrangian multiplier here is adjoint variable, like U is a adjoint velocity or Q is a adjoint pressure. So derivation of adjoint equation is not easy and it's time consuming. And this is one of the disadvantage of adjoint method, because for each objective function, the adjoint equation must be derived again. However, after derivation, for each optimization cycle, only two set of equations should be solved, regardless of number of design variables. And then this is the final form of adjoint Navier-Stokes equation. So simple foam solver, which is a 3D steady state incompressible Rand's equation, is used as a solver in OpenFOAM. In order to discretization in a space, a fully second order method is used. Also for the pressure velocity coupling, the simple technique is employed. Since we simulate in a steady form, MRF model is employed for adding the effect of impeller rotation. The mass flow rate of 0.1 is imposed to the sphere as an inlet, and the initial value for rotational speed is set to 277 radian per second, and the static pressure of 83 Pascal is imposed to the outlet. So an unstructured mesh grid with tetrahedral element is generated. The maximum Y plus around impeller is 1. In order to find the efficient mesh grid, 3 different mesh grids are created, and they compare to each other in terms of total efficiency, which is defined as a flow rate to pressure rise over torque multiplied in rotational speed. The result of total efficiency between medium and fine grid is approximately 0.5 percentage. So medium grid with less mesh cells, around 14 million cells, is used for subsequent computations. For the adjoint method, two different objective function is choose. The aerolic power is it should be maximized, and the mechanical power should be minimized, resulting in an improvement in total efficiency. Since we have more than one objective function, we must consider the weight of the objective function, so we set the weight 50-50, the same weight for both two objective functions. This is the multi-objective framework that is developed in my research based on the adjoint method. So two new objective functions are defined, and it starts with creating geometry and then create the mesh for the computational domain. Then flow equation will be solved, and then rotational speed change in order to find the proper value to satisfy the target pressure. This rotational speed is stored because we need it to calculate mechanical power, and also the initial values of both mechanical power and aerolic power will be solved for the first time. And then adjoint equation will be solved. After solving the adjoint equation, sensitivity can be solved for the impeller easily. And then we have some Python script to compute the average sensitivity and also averaging and smoothing the results. So here, optimization of two different cases with adjoint method help us to be more familiar with adjoint method and adjoint solver before we customizing the solver. The first case is a simple case, is a sphere with a diameter of 5 millimeter. We create on a structure mesh with 25 prismatic layer, and the maximum Y plus around a sphere is around 1. And also the velocity of 60 meters per second is imposed to the inlet. The sphere is optimized in terms of drag reduction. Also, we consider geometrical constraint for it. It's like a partial volume. We use the base B-spline, volumetric B-spline as a parametrization method to modify the shape of the geometry based on the information of gradient. And we test different control points configuration, and this one with 343 points is the efficient one. We have 7 control points in each direction. So after 22 iteration, the drag force is decreased by 14%. As you can see, the weight behind the optimized one is a bit smaller than the initial sphere. After that, we choose more complicated geometry compared to a sphere. We choose to optimize autonomous underwater vehicle, which is the cutting edge technology in maritime engineering. It has different kinds of application, like in ocean exploration. But one of the challenge they face is that they only can operate for a short time. So in order to tackle this problem, we need either to have more powerful batteries or reduce the drag force. One of the way to reduce drag force is that to optimize it in terms of doing shape optimization for AUV. So the novelty of this work is that there is a lack of a study on AUV shape optimization using the adjoint method in the literature. So two different geometry are chosen. The first one comes from the work of Alam that was initially designed by Metamodels. And the second one comes from the work of Sagafi with manipulating the equation of nose and tails and test it in order to find the geometry with the lower drag force. Design variables with their values are shown in this table. Both test cases have the same lengths, 1.3 meter, and also the same diameter, 250 millimeter. We only focus to optimize only nose and tail, and midsection doesn't change since many facilities are placed there. It is embedded in a cylindrical computational domain, which is aligned with the midsection of the AUV. The velocity of 2 meters per second is imposed to the inlet, and also create another unstructured mesh with 26 prismatic layer for the geometry. In order to find the efficient mesh grids, 5 distinct mesh grids are created and compared in terms of drag force. The drag force comes from grid 3 and 4 and 3 and 5. It's negligible, therefore we go for the rest of computations with medium mesh grid with 2 million mesh cells. As you can see in two previous works, numerical works, they use Ka epsilon turbulence model, but in the current study we use Ka omega SSD, and it shows a really close value for objective function to experimental result. It's about 0.5% difference. Like a sphere, in order to change the shape of the geometry, we create 2 different control points around the nose and tails, which has 4 points in each direction. Before delving into optimizing, we check and simulate both AUVs in different angle of attacks. As you can see, with increasing the angle of attack, the stagnation points moves below, and the stall angle is not observed. So maybe it happens after 20 angle of attack. Sorry. Two different scenarios are taken into account for optimization. The first one, unconstrained optimization, where the drag force is chosen as an objective function, and in constraint one, we have a partial volume as a constraint. Well, we cannot see a huge difference between initial and optimized ones, since they have been optimized before with different method. By the way, in unconstrained optimization, the first AUV, drag force of first AUV is reduced by approximately 4% after 7 optimization cycle. And compared to baseline, the optimized nose is thinner. The high pressure region around nose for the optimized one is diminished compared to initial one, and also the vorticity behind the tail of optimized one is smaller. For the second AUV, the drag force is reduced by 2.6% after 4 optimization cycle. Like the first AUV, the nose of second AUV also becomes thinner compared to the baseline. So in constraint optimization, first AUV shows around 3% drag reduction after 9 optimization cycle. The optimized one has a thinner nose, but almost the same. For the second one, also the drag force is reduced by 2.6% after 4 optimization cycle. As you can see clearly, the wake behind the tail is diminished for the optimized one. So here we have a comparison between the optimized first and second optimized AUV in a constraint optimization. So generally, the first AUV has a higher drag force compared to second one, and it can be defined by the separation flow around the tail of the first AUV, and also higher pressure region on the tail. So in part 5, the results of the main part of my research will be present, which is related to design and optimization of the forward curve centrifugal blower. First, in order to design blower based on gradient-free approaches, 11 design variables associated with both impeller and housing are chosen. So table shows the lower and upper bounds for each design variable. So this framework also works automatically without user intervention, and we use the LHS as a design of experiment and some meta models to find the efficient blower. It starts with importing the data of design variables and their bounds into the Dakuta, and Dakuta employs LHS in order to create different samples. All samples will be created by Salome, and there is an inner loop to check all geometries. And then mesh will be created again by Salome, and the quality of the mesh will be checked by the tool in OpenFOAM. After solving the flow equation, post-processing will be done in order to get the value of objective function for each design variables. For the meta model, we use the LHS sample to create the model to predict the efficient blower. So here in the first part, since we have 121 samples obtained from LHS, I compare the two samples that have lowest and highest efficiency. So there is around 19% difference in efficiency. And also after that, you can see the highest efficiency that obtained from different optimization methods. Gaussian process, which is a surrogate model, shows the highest efficiency, and the result is validated against CFD model, and it shows around 0.2% difference. Then the blower is offered by GP, Gaussian process is manufactured, and the numerical results are validated against experimental results using fan curve, and it shows good agreement. So here the results are related to agile method. So for now, the framework based on agile method can optimize the impler, not housing. So after obtaining the sensitivity result of the impler, it shows us how we need to change the shape of the geometry as normal to the surface. So if the sensitivity is positive, means that the point must go outward normal to the surface. If we want to modify the shape of each blade based on its sensitivity, it creates an imbalanced impeller, which is not the case in a real world. So we need to averaging the sensitivity for each blade. Also, the deviation shows that the sensitivity is important since we have high fluctuation, especially on the middle of the suction side. I don't put the pressure side because they have the same pattern. So in order to averaging, we need first to use the interpolation, and because each blade has on a structure grid and unique grid. So after we choose one blade as a reference and map all the blades on it, we can easily average the sensitivity. Almost they have the same pattern, I mean the pressure and suction side, but on the pressure side we have more bigger changes in sensitivity, but we cannot see any negative sensitivity. It shows that the blade should be thinner. And since for now the framework cannot create the 3D blade, we need to also average in Z direction to get the profile of each blade. So after 4 optimization cycle, as you can see, the aerolytic power increased by 0.7, and also mechanical power decreased by 0.5, and it gives us around 1.5% improvement in the efficiency. In order to modify the shape based on the sensitivity, we set the displacement at 0.1 millimeter for the profile. This is the final shape of the initial and optimized profile. As I mentioned, it become thinner in both sides, but since we had bigger changes, bigger value for the pressure side, we have it become more thinner on that side. So here we can see the dimensionless velocity magnitude. It is clear that we have a low velocity zone close to the time, which is diminished for the optimized one. And also we can see that the pressure on the blades for optimized one is recovered, and it is more uniform, resulting in better efficiency. Well, for conclusion, we start with optimizing a sphere using the adjoint method, and it showed 14% reduction in drag force. For the AUV, first we validated against experimental data in the literature, and it shows about 0.5%. In unconstrained optimization, first and second AUV showed about 4% reduction in drag force. For the constrained one, they show both cases showed about 3% reduction in drag force. For the second part, first we design an efficient forward curve centrifugal blower, and the Gaussian process method offers the blower with highest efficiency. Then the results of the efficient blower was validated against CFD and experimental result. Then I proposed a new automatic multi-objective framework based on the adjoint method, and both objective functions showed around 0.7% increase and decrease in aerolic and mechanical power respectively, which result in a 0.5 improvement in total efficiency. Future work for the gradient-free approach, the framework. For modern turbo machines, it is important to have different operating points. So it is important to add multi-point optimization to this framework. To optimization AUV, the length, the ratio of length to width is important for reducing drag force. So it can be a potential research for future, and also adding proportion to the aft of the AUV can make it closer to the real test case. And it is interesting to optimize AUV in terms of noise reduction. For the gradient-based approach, as I mentioned, now it can create the blade using the profile and extrude it in a Z direction. So in order to have more accurate result, it is important to add 3D sensitivity to the framework, and also the adding housing to the framework for optimization, because now the focus is only on impler. And also the ability of the optimization of the blower in terms of aeroacoustics. So the research of the result of this research is it has been presented and published in different conference and journals paper, and the last paper from the optimization of the blower using the adjoint method is on the preparation. In the end, I want to thank my supervisor Sebastian and co-supervisor Bernard and all my colleagues in our group, and also a special thank to Raymond to financially support this project, and also Wenmar as an industrial partner. So for sure, visit cluster, especially Narwhal. I couldn't do this, all of this simulation, and also I have used bunch of open source software. So thanks to all of them.